Okay, let's learn about histogram of oriented gradients, also known as HOG, also known as HOG descriptor. So we saw in our previous coding example that HOG descriptors is nothing but a process of converting our image into some kind of a feature vector which is required for machine learning algorithm, which happens to be SVM in this particular case. So we saw that the process of getting an image, which is nothing but a two-dimensional array of pixels into three channels. Into first we get a crop. We crop out the face of the cougar. That is what we want to detect. So and then we get a HOG descriptors, right? So basically what we did was here from this image we had the bounding box, right? That was given to us along with the image. Using this bounding box, which is nothing but the coordinates of the face, we draw the bounding box around the cougar face. Then we crop out only that part and then get this image, and then this image we convert into a compact representation called HOG descriptor, which is nothing but 3780 dimensional vector, which we are going to feed it to the machine learning algorithm. So that is what we saw. Now let's go into detail on how this vector of 3780 dimension gets generated. So it's a multi-step process. We will go step by step. So step one is basically pre-processing an image. So here what we do is we have this image of a cougar. Then we have these bounding boxes that were given to us, which has the XY coordinates of the bounding box, right? So we use those XY coordinates to draw the bounding box, right? So this is basically height, which is h here. This is nothing but the width, which is w here. X is, so let's say if this is the x-axis and this is the y-axis, x is this distance, y is this distance, right? So using these four coordinates we can draw this bounding box around the cougar face, and then we crop out that cougar face into another image, usually of 100 by 200 size. We basically compute that image, and if the image is of not that size, then we resize that image, because usually if we resize the image where um, the height is double the width, that works well for the machine learning algorithm in this particular case. So this we resize to 64 by 128, right? And that's what we use in our step 2. So step 1 processing is crop out the cougar face which you want to detect and resize the image to 64 by 128. Okay, the next step is we need to compute the gradient. So why compute the gradient? If you take a look at this cougar image, there is a lot of information which we really don't need, right? So for example, if you see this background over here, for example, if you see all this background, which we don't need, right? It is not really conveying any information. So what we do is we compute a gradient, right? A gradient is nothing but a directional change in the image intensity. So what we do is we take the image, we start scanning from left to right and then from top to bottom, right? And let's say we take a smaller area like this, right? Like the 3 by 3 area, right? And in this 3 by 3 area, we monitor how much the intensity has changed as we move from left to right and top to bottom, and that intensity is captured into the gradient. So as a part of, and we do same thing as we and then we move this patch to the right, we repeat the process. Then once this rotation is finished, we move this patch down and they repeat the process. So, and we compute the gradient by convolving it with filters called Sobel filters. So the result of this computing gradient is we get only the pixels which indicates the change in the image intensity, right? So as we can see, wherever the image intensity is changing, right from the background to this ear of the cougar or the mouth of the cougar, that part the intensity is high, right? And rest of the part intensity is low. So this ends up in drawing a contour or the highlights where the image intensity is suddenly changing, and that part we are interested in capturing, because that really represents the change in the image intensity, which is nothing but called a gradient, right? So the way to do that is we use a convolution operator that I just explained earlier, where we take these Sobel filters which are predefined 3 by 3 matrix, horizontal and vertical direction, and then we move them from left to right and top to bottom and convolve with the pixels of the image and compute the gradient. And this is the code for that. So we read a image using OpenCV. This will give me a three-dimensional, basically three channel and two dimension. Each channel is two-dimensional array of pixel intensities. We convert it to grayscale. Then we compute the gradient using cv2.sobel method in x and y direction. And the overall gradient has two things. One is called, so gradient has two attributes. One is the magnitude, which represents the intensity, the actual magnitude, and the other one is the direction, which indicates in which direction the intensity is changing. And we compute that magnitude and direction, and we can print it out and you can plot it. So what we saw was in the previous direction, this is the magnitude of the gradient that we can plot, and this is what we will use in subsequent steps. Okay. Now the next step is, once we have this gradient, the next step is we compute the something called histogram. So as you saw, this image size is 64 by 128, which means it has 64 rows, and it has 64 128 rows and 64 columns, right? What we do is we divide this image into 8 by 8 patch, right? So that means this will have 8 columns, 1 2 3 4 5 6 7 and 16 rows, right? So I'm going to draw like this. Okay. So in each patch is basically nothing but 8 by 8 pixel array. Okay, that's what we do first. Once we have this 8 by 8 array, right, we compute gradient. We know we compute the gradient for this patch. So this patch will look something like this, right? So if you know the magnitude and directions, so as you can see, if you plot it and expand this, it will look something like this, right? In basically visually, right? This will look something. So this is an 8 by 8 patch. Okay, so what we do is, for this 8 by 8 patch, we compute magnitude of gradient, which will be 2 3 4 5 6 7 1 2 3 4 5 6 7 8, and also 2, 3, 4, 5, 6, 7. We can draw this side 7 and 8. So okay, this is 8 by 8. So this is a magnitude, and then we have a direction. This also will be 8 by 8. 1, 2, 3, 4, 5, 6, 7, 8, and again there will be 8 rows. 1, 2, 3, 4, 5, 6, 7, and 8. We can draw here. So this also will be an 8 by 8, and this is the direction. Okay, so the magnitude will represent the intensity, which will be in the range of 0 to 255, and this 8 by 8 direction will be the angle of that patch. For example, this intensity patch could be oriented in the direction of minus 45 or plus 45. So this angle will range from 0 to 180 degrees for each pixel, right? So we compute these two pixels, which are nothing but magnitude and direction for each 8 by 8 pixel, right? Right. So once we do that, what we will get is, let me draw it again. Okay, so 1, 2, 3, 4, 1, 2, 3, 4. So I'm not going to draw everything, judge a few examples. So this is 8 by 8 magnitude. This is 8 by 8 direction. Okay, again it will be 8 rows and there will be 8 columns. 8 columns. Okay, so now what we do is we combine these two values into 9 beans. Okay, which means each of the bean represents angles. This is angle from 0, 20, 40, 60, 80 up to 160. Okay, so now what we do is we map these values into these 9 beans. Okay, so for example, let's say we have a pixel here whose value is let's say 5 and the angle is 80. Okay, so this value and this pixel will, that means the 5 will go into this pixel, right? Yeah. Now let's say we have the another value called 4 and it has an angle of 10. That means that value needs to be equally distributed between these two. So half of this will go here because angle 10 is midway between 2 to 20. So 4 will be divided into 2 and again it will be divided into 2, right? So we keep doing that and we keep adding the values. So eventually what will happen is, what tends to happen is, once we do that, you can plot a histogram of those 9 beans, right? So you will get a histogram like this for each of those 9 beans, like 0, 20. You can sum up the values and you can calculate, right? Something like this you will get a histogram up to 160, right? So this is the process of computing a histogram from the gradient. So basically this represents what is the distribution of each angle and the corresponding magnitude in a specific direction. For example, as you can see, there is a lot of pixels around 0, 0 and 180 degree at the end. This means in this particular case there are a lot of pixel gradient which has an angle of 0, right? Yeah, that's what it is. So we saw earlier how an 8 by 8 block is converted into so we saw how 8 by 8 block was converted into 36 by 1 vector, right? So normally the next process is normalization. Okay, so normalization is, so let's say if this is the vector which has the value of 10, 20 up to 36, the normalization is dividing all of each of this member. So let's say if this is x, we divide each of the value by a factor which is the root mean square of all the values. Right? That's the process of normalization. But this normalization is not done per 8 by 8 patch. Instead, that what they do is they collect 16 by 16 patch. So if each patch is 8 by 8, they cover like 16 by 16 patch, and then for 16 by 16 patch they normalize it, right? So for 16 by 16 patch and what they do is for 16 by 16 patch they do the normalization, right? So and what they do is once this block is finished, and remember this is this whole image size is 64 by 128. Okay, always remember this. So and then what they do is they take next, then they move the square to the right and they take next 16 by 16 block, right? So these are overlapping, and then they take next 16 by 16 block. So they keep repeating the process by moving the 16 by 16 from left to right and top to bottom and compute the vector at each point. So if you calculate how many 16 by 16 patches are there, so if you move the left, there will be 7 columns and 15 rows of 16 by 16 patches, right? Remember they're overlapping, so you need to include that overlapping way also. So there will be 7 columns and 15 rows of 16 by 16, right? And for each 16 by so there will be total patches will be 7 into 15 will be 105. Yes, and for each 105, which is a patch of 16 by 16, will compute a vector of instead of 9, they will now for each patch of 8 has 9 bins vector. So for 4 patches will be 36. So for each patch, if there are 36 a vector of size 36 is created, then total number of elements in the vector is 105 into 36, right? So that will become 3780, right? So this is the dimension of the final vector. Again, let me repeat. So we have original image size of 64 by 128. We compute a patch of 16 by 16 block. For each 16 by 16 we compute a 9 bin vector, which means it will become 36 because there are 4 8 by 8 blocks in it. And then we move the area to 1 row and 1 column at a time, to the right and to the from top to bottom and from left to right. So we end up covering 7 16 by 16 patches in the horizontal direction and 15 16 by 16 patches in the vertical direction. So there will be 105 patches total in, and each patch of 16 maps to a bin of 36 that we saw, and the total number of dimensions for the final vector will be 105 into 36, which happens to be a 3780 vector. So this is how we compute a 3780 feature descriptor for an image, and this really represents a compact representation of the image that we use in the dlib library.